has discovered 3 new particles which could help learn how our universe was born and what its future looks like.
And this opens a new era of exploration at Cern, a new chapter.
The cosmos is full of mysteries, and scientists are just scratching the surface. There are so many things we're discovering that need new physics theories to make sense of them. Take gravity, for instance. It's way weaker than the other forces in the universe. Then there's the big one. What happened before and during the Big Bang? Among tons of other things we're still trying to figure out. But thanks to new technology, we've made progress. Cern, in particular, has been leading the charge. And now, the team of scientists at Cern have recently made a discovery that's so terrifying and groundbreaking, it could rewrite history and change everything we thought we knew about the universe. The Higgs Boson and particle physics revolution. The Large Hadron Collider, LHC, is the heart of scientific exploration at Cern, which stands as a major European institution born after World War II. It's a hub that draws in scientists from across the globe. Its primary function involves accelerating protons to high speeds and smashing them together. These collisions occur within massive detectors situated in subterranean caverns, allowing scientists to analyze the outcomes and glean insights into various phenomena. The main reason they're doing this is to figure out the basic parts of the universe and how they all fit together. It's like super basic science stuff. For a long time, scientists were excited about finding the Higgs boson. Back in the 1960s, a British physicist named Peter Higgs thought there was this field making particles heavy. He said there should be a particle connected to it, and that particle would give mass to all the others. In a 1993 book, they called it the God particle. But lots of scientists don't like that flashy name. They've been looking for this Higgs boson, and after many years of searching, the LHC made a big find in 2012. They spotted a teeny particle in an atom center, and get this, it was about 126 times heavier than a proton. In less than a year, scientists were super happy because they figured out that the new particle they found was the Higgs boson. They did this by carefully gathering loads of data, collecting about 2.5 times more info thanks to the powerful Large Hadron Collider. Now, in the world of particle physics, this discovery was like finding the last piece of a big jigsaw puzzle called the Standard Model. This model explains how tiny things like forces interact, but there's a catch. It doesn't cover gravity. 2 brainy folks, Peter Higgs and François Englert, bagged a Nobel Prize in 2013 for figuring out the Higgs boson and saying it existed. According to Professor Victoria Martin from the University of Edinburgh, this find completed the Standard Model puzzle. It was like the missing link, and it shook up particle physics, opening doors that were shut tight before. Gian Giudice, who heads up the theoretical physics squad at Cern, made a bold statement on June 30th. He said that in the last 10 years, the whole game of particle physics changed more than it did in the 30 years before. One big reason everyone's excited about the Higgs boson is because it's like a carrier for something called the Higgs field, kind of like how photons carry the electromagnetic force. According to Martin, this field is super important. It's more basic than the particles themselves. It's like this invisible force that stretches across everything, all across space and time. So this Higgs boson, which is like a symbol for this field, interacts with certain particles, giving them their mass. Think about electrons, they're tiny in mass, or photons, which have no mass at all. They can pretty much ignore the Higgs field and zip around at light speed. But for the heavier particles, it's a different story. They've got to trudge through this Higgs field, which slows them down, making them more massive. So those heavyweights in the particle world owe their mass to this cosmic muck of the Higgs field. Scientists haven't seen much happening yet, but they're pretty sure this is how things roll in the particle universe. But that's not all. Unveiling mysteries of mass and energy with LHC. The Higgs boson, just like those other particles, supposedly gets its weight by mingling with itself. It's got a mass of about 125 billion electron volts, which is a hefty 125 times more than one of those positively charged protons chilling at an atom's center. The Large Hadron Collider did the measuring here, and when these physics whizzes talk about mass, they're referring to its energy, thanks to Einstein's special theory. Now, apart from this big discovery, there's still a lot we don't know about the Higgs boson. It's like we've only poked a finger into what it can do. Martin says the last decade was all about testing this Higgs boson. But hey, the Standard Model, our current best theory of how the tiniest bits of nature behave, gives us a pretty good idea of what to expect from this Higgs boson. You see, the LHC's job is to put this Standard Model through the ringer, testing it at the tiniest scales and highest energies ever messed with in a lab. But here's the kicker. The Standard Model isn't perfect. It has some trouble describing this super strong force that holds atoms' cores together. The heart of an atom, its nucleus, is made up of protons and neutrons, and each of these is made of 3 tiny particles called quarks. Now, there are 6 types of these little fellas: up, down, charm, strange, top, and bottom. Here's a wild thought. If the strong force, which holds these quarks together, took a coffee break, all matter would turn into a soup of loose quarks. This happened for a flicker of a moment at the start of the universe, way back when things were just kicking off. Now, this strong force, often called quantum chromodynamics, has its groove in the physics world. It explains how this force pals around with quarks by passing these bits, called gluons, between them. You could think of gluons as sort of like photons, those particles of light that carry the power of the electromagnetic field. But here's the twist. The strong force, with its gluons, plays by different rules compared to electromagnetism. When you pull apart charged particles, the electromagnetic force gets weaker. But when you try the same with quarks, the strong force gets stronger. So, these quarks end up stuck inside these things called hadrons, which are like little quark teams made up of 2 or more of these particles. And unless you give these hadrons a super speedy smack, like they do at Cern, those quarks are sticking together for the long haul. In the Standard Model of particle physics, every particle has a counterpart called an antiparticle. These antiparticles are almost like mirror images of the regular particles, but they have the opposite charge. To make things even more interesting, they also have other quantum properties that mess with our understanding. Here's a quirky scenario. If you take a proton and yank out a quark, an antiquark is born. The new proton that forms will then absorb this antiquark, resulting in a proton and a fresh particle called a meson. This meson is a combo of a quark and an antiquark. It might sound a bit odd, but in the world of quantum theory, particles can pop into existence seemingly out of nowhere, especially when you're dealing with the tiniest scales in the cosmos. This is just about to get more interesting. New insights into quarks and particle bonds. The Hadron Collider has recently unveiled 59 new hadrons, which include fresh mesons and baryons, alongside the latest tetraquarks. These newcomers are all packed with heavy quarks, like bottom and charm. Exploring these hadrons is like diving into a mystery novel. These quarks give us insights into what nature accepts as a bound quark pair, even if it's just for a fleeting moment. They also tell us what nature seems to avoid, like why do all tetraquarks and pentaquarks have a charm quark pair? And have you ever wondered why there aren't any strange quark pairs in the mix? While we're scratching our heads over these questions, one big mystery remains. How does the strong force keep these particles together? Some theories think they're similar in size and shape to protons or neutrons, while others suggest they're more like molecules made of 2 loosely connected hadrons. Each of these newly discovered hadrons is like a piece of the puzzle. By measuring their mass and other features, scientists can gather info on how the strong force behaves. This helps fine-tune our models to match what's happening in the real world. In other words, the more hadrons we uncover, the better we can understand the strong force and how it plays its part in the grand scheme of things. The Hadron Collider has a big goal: to dig into physics beyond the standard model. While the model of particle physics has done a lot, it's not the whole story. There's a snag. The standard model doesn't quite match theories about the universe's birth. The Higgs boson is a mystery in this puzzle. Unlike every other particle, it lacks quantum spin. Martin and her team are trying to crack this to test the standard model's limits. The Higgs field, where the boson hangs out, is mysterious. Unlike forces like gravity or electricity, it's elusive. It's everywhere, linking space and time like an invisible thread. Here's a kicker. Both the Higgs boson and the space-time vacuum share this lack of quantum spin, even though the vacuum isn't as empty as it seems. In the quantum world, things get wild. Particles pop in and out of existence, jazzing up the vacuum's energy beyond its basic state. Everything in the universe, from a person in gravity to an electron in an atom, aims for its lowest energy level. But here's where it gets interesting. Our universe doesn't follow the usual rules. Scientists talk about this energy potential in the Higgs field. It's like the cosmic superhero that stops the universe from losing energy and going downhill. Imagine this energy situation like a graph with a mountain in the center and two valleys on either side. One of these valleys has the energy level of the vacuum. However, physicists are pretty sure there are deeper valleys on each side of those hills. And guess what? These deeper valleys have even lower energy states. The mass measurement of the Higgs boson backs up this idea. The size of this particle suggests that the Higgs field has some room to eventually chill, at an even lower energy level, like sliding down a cosmic slope. The Higgs field's cosmic balance. The Higgs boson is a bit like having a superpowered microscope and a high-tech telescope all rolled into one. It helps scientists peek at the tiniest bits of nature and also explore some seriously high-energy physics. This particle is linked to something pretty wild, our vacuum. Now, when physicists talk about our vacuum, they call it a false vacuum. Why? Because it's itching to drop to a lower energy state, a truer vacuum. But hold on, our universe is kind of hanging out in this fake vacuum, thanks to the ups and downs in the energy potential of the Higgs field. This false vacuum has been chill enough for planets, stars, and galaxies to do their thing, but here's the catch. It's not stable. This fake vacuum is like a ticking time bomb, slowly falling apart. It might try to sneak over these energy barriers or even tunnel through them, thanks to some funky quantum quirks. If this false vacuum crumbles, picture a wave of destruction zooming at the speed of light, wiping out everything and replacing it with the real deal, a true vacuum. And that wouldn't be good news for the universe. Luckily, we've got the Higgs field to thank for keeping things in check. It's the unsung hero holding our cosmos together, preventing this vacuum catastrophe from happening. Scientists have been on a quest for the past decade to figure out how long the Higgs boson sticks around before it breaks apart, and also to understand its spin. According to the standard model, this boson is supposed to exist for an incredibly short time, just about 10 to 22 seconds, before it breaks down into smaller subatomic particles. But here's the catch. This prediction hasn't been confirmed by experiments yet. The LHC's third operational run, called Run 3, which kicked off on Tuesday, July 5th, is expected to be a huge milestone in this quest, at least according to the scientists. Martin mentioned that they're hoping to somehow measure how long the Higgs boson lasts indirectly. If they can nail that down, it could narrow down the possibilities of what particles the Higgs boson breaks into. Understanding how the Higgs boson breaks down into different particles might unveil new subatomic players, possibly including dark matter particles, which are a bit of a mystery. Gennady pointed out that because of these possibilities, the Higgs boson becomes a crucial tool for diving into the most puzzling bits of particle physics. The significance of this particle goes beyond just another task on physicists' lists. Its existence and behavior trigger fundamental questions in physics. It sheds light on critical aspects of our universe, its stability, and the interactions of elementary particles, raising some of the deepest mysteries. Understanding how the Higgs boson connects and interacts with the Higgs field to acquire mass is one of particle physics' greatest puzzles. Solving this enigma could provide insights into why the early universe had more matter than antimatter. This imbalance is crucial, because if both existed equally, they would have destroyed each other, preventing galaxies and stars from forming. But that's not the most interesting part. Amplifying the hunt for rare Higgs boson patterns. Researchers at Cern are hunting for rare behaviors in the Higgs boson, specifically pairs and triplets of these particles. These unusual interactions, known as self-coupling, are extremely scarce, even more so than single Higgs particles, predicted to be about 1,000 times rarer. To delve deeper, the LHC is undergoing a high luminosity upgrade. This boost in collisions will ramp up Higgs boson production, potentially increasing the chances of spotting these rare occurrences. The plan is to compare Higgs boson production before and after the full operation of the high luminosity LHC in 2029. In 2017, the LHC generated around 3 million Higgs bosons, but the upgraded version is anticipated to produce about 15 million annually. This significant increase aims to drive more discoveries about the Higgs boson's behavior. Dark matter remains a strong indication that there's more to physics than the standard model explains. Although dark energy holds more influence in the cosmic balance, dark matter constitutes over 80% of the universe's mass. Its gravitational pull holds galaxies together, but it doesn't interact with regular matter or electromagnetic radiation. The Higgs boson plays a key role in giving particles their mass. As dark matter particles likely have mass due to gravity, they might interact with the Higgs field. When Higgs bosons break down, they could leave behind a trace of dark matter, linking their discovery to unlocking this cosmic mystery. This connection suggests that understanding the Higgs boson, discovered after a monumental effort, may be the key to understanding dark matter. Despite the excitement around the Higgs boson's discovery in 2012, it seems to be guarding its secrets. Observations align with the standard model, but scientists hoped it might open new paths. Moving beyond the standard model is vital to explain anomalies like dark matter and explore theories like supersymmetry. Rather than breaking rules, scientists aim to extend them. Hence, the LHC is preparing for another phase to uncover the Higgs boson's mysteries, potentially leading to groundbreaking discoveries in physics. The pursuit of these answers continues, driven by the hope of uncovering something revolutionary. However, a recent revelation about our sun is getting people worried about the activities at LHC, unveiling cosmic secrets and conspiracy theories. In a surprising twist, scientists have split the beans that our sun is getting ready for a super-active phase in its solar cycle, showing up earlier than expected. This is like a celestial party favor for people who love staring at the stars. There's a better chance of catching those breathtaking auroras in the next 3 years. But as scientists cheered about this, the LHC did more than just unlock universe secrets. It somehow became the center of a lot of interest and worry. As folks dug deeper for answers, there were some who started wondering about what might happen if we mess around too much with the mysteries of the universe. The LHC, which is all about helping us understand the universe, got tied up in concerns about the unknown. Some people, way deep in their imaginations, think the LHC might be like a secret doorway to another world where demons and nightmares could sneak through. Others have this wild idea that the LHC is hiding a megaweapon, ready to wipe out our whole planet if someone decides to press a button. Then there are those who love spinning complex stories. They suggest that the LHC is part of this big government plan, like a secret experiment to control our minds and turn us into mindless robots. According to these theories, the particle crashes in the LHC aren't just about science. They're secretly trying to set up a whole new world where only fancy folks get to survive. Do you believe that the recent discovery by physicists at Cern will revolutionize our understanding of the universe? Let us know in the comments below.